All right. Sit up. Okay, there's another thing I want to mention before I start teaching today. So one of the students in our class can talk to me in the morning, asking for a recommendation letter for something. All right. So I want to tell you is my policy on writing a recommendation letter is pretty much unlimited. All right. There's nothing stopping me from writing you a recommendation letter because I think that's a perfect example, a perfect way to help you in terms of advance your career, right? So in the future, if you need a recommendation letter for your internship, for your research position, or for your job, or anything, feel free to let me know, all right? So just send me an email, and then one of the things I always do is, which is happened to me too. So when I ask for a recommendation letter from other people, the first thing they ask me is two things. They asked me to draft a letter for them, and also they asked me to attach my resume or CV, right? Because the best person who knows yourself is you, right? Is yourself, right? So if you ask me for a recommendation letter, I'll be happy to do that, but make sure you draft me a letter, and if you need some sample letters, feel free to let me know. I think I wrote about 52 letters since I came here, right, for students. So I have lots of sample letters, which a lot of them are good. So feel free to let me know, okay? All right. So let's see. So today we are going to go through a big example, and the example combines bending moment and torque and applied force, right? So it's a very big example, which summarizes all the stuff we learned so far, okay? All right. How's my writing? Okay. But anyway, okay, so if we have a crank, it's loaded by force of F equal to 300 newtons. I think my problem is I write too fast. If I write fast, it gets ugly, right? So I'll try to write it slow, right? But the reason why I write fast is because the first class I was using this. I was also teaching graduate level class. The graduate student told me, say, hey, when you use this, you teach so slow, so write fast. So I guess for them, I just write fast. Who cares whether they can recognize my writing or not, right? But for you guys, I write slow. How's that?
Copy paste the picture.
Copy paste the picture? Sure. We can do that. Yeah. I'll try it this time. All right.
I got a smaller one.
You got a smaller one?
I don't know if it makes a difference.
All right. If it's good, I'll keep it. All right. I think it's better. Yeah. Okay. So it's on the static. All right. There's no movement at all. Now it's ask us to find basically get what you pay for, right? I'm using a free stylus, so no wonder, huh? So first of all, to draw free body diagram of beam AB and BC, and compute the value of all forces, moments, and torque that act, and also ask us to label the direction of the coordinates axis on this diagram. B, compute is the writing getting worse? Oh man, what's your name? Alright. Okay. I'll read it. Alright. So draw free body diagram of AB and BC and calculate the value of all forces, moments, and a torque that act. So basically the force on it, alright, and also the moment on it and the torque on it. So label the directions of the coordinate axis on this diagram. So because for force, moment, and the torque, they have directions, right? Force is a vector, moment is a vector, and torque is also a vector. So they have directions, okay? So which word I wrote terrible? Tell me. Label? Where's the label? Oh, lab? Well, that we cannot blame on. I don't know your name. You keep on telling me the different names. Okay, that we have to blame on me because I don't speak English, right? So, anyway, okay. The second one is compute the max, or maximum of torsional stress. And bending stress. In BC. And indicate where they at. Okay, so all right, so I guess let me try to take a picture of the figure so I don't have to draw it, right? Let me turn on the lights. I don't have a book, I'm sorry. That's why I don't ask you guys to buy a book, right? Who wants to buy a book? It's so expensive. I'm going to try to take a photo of this thing so we can see it better. Let me try to turn it off. Can you guys see it?
Yes.
Over here, actually, let me move it. So just focus on this. So there's three beams here, A, B, and BC, and CD over here. I guess in the future I'll try to take a picture from the book, huh? And the diameter of the AB is 3/4 of inch. Meter, and the length of the AB is 5. And from BC over here is 4 meters long, and it has a width of 1/4 meter and a height of 1.25 meter. And the distance from point C to the point where we apply force is 1.5, and this rod over here at the end is 1/2 meter in diameter. So that's pretty much it. Okay. All right. Next time I'll try to bring the book, and I can take a picture from the book. All right, which is way better.
What problem is it in the book?
I can't remember. Sorry. All right. Now I'll let you draw the figures. So. Okay. So there's only one force applied, all right, at this beam, this ball over here, and the only boundary condition is it's fixed to the wall. AB is free, BC is free, and this small rod over here is also free. Huh?
For the middle bar, it says 114.
This one here? Yeah, 1.25. Let me try to make it bigger. This one is easy. Okay. Most of you are done with the drawing? Okay. All right. So, let's see here. Are most of you done with the figure drawing? Very much? Okay. Okay, so the first thing I want to do is, by looking at it here, I know there's the force is initially applied on this bar, right? On this cylindrical bar. So I need to start my analysis from here. Okay? All right, so let's see over here. First of all, this force is 300 newtons. Now I am only looking at this, all right? So when I do free body diagram, everything becomes a one line, right? I'm not drawing the entire thing because just to simplify things. So the force is 300 newtons. Okay, now you will have a resultant force going upwards, and in the same time, because here's what you do, right? 3 components, A, B, that's the first one, B, C, the second one, and then lastly, this small ball, right? So 3 components. So we start with a small ball, and the small ball actually, since everything is anesthetic, it has a condition very similar to cantilever beams, right? The end point C is fixed, while here you have free end, so that's cantilever beam, okay? For cantilever beam, when you take away the support, you have 2 different resultant reactions. One is this force over here. Let's just say this is a C. Let's just say this is F. All right, at a point C. In the same time, it is going to have a moment. Let's say this is MC, right? To balance for it, because for cantilever beam is like that. Okay, now you see this coordinates goes like X, Y, and Z, right? Use your right hand rule. So start with X, turn to Y, your thumb is Z direction. Okay, so this is your coordinates. Okay, now remember in statics, or also in mechanics of materials, for directional vector, we use I, J, and K. Right? So I is a unit vector which is aligned with positive X. J is a unit vector aligned with Y. K is a unit vector aligned with Z. Right? That's the unit vector. Okay. The reason why we're doing that is because this time it's a 3-dimensional problem, and it is asking us to determine the direction of the force, moment, and torque as well. Okay. So by seeing that, I know this 300 newtons, it is in the direction of negative y. See here, y is going up, this 300 newtons is going down. See here, right? So therefore, I know the 300 newtons, probably it has a direction of minus j, right? Okay, so therefore, summation f is 0. I know this fc got be 300j newtons, right? Because summation f is 0. The only force in the system is fc, and this applied for 300 newtons. Okay. All right. So fc is solved. And how about m then? So let's see here. Summation n has to be 0. Therefore, I know. Now, as you know, the direction of the bending moment, see, 300 newtons is going downwards. Imagine this is your rotational center, right? So 300 newtons going downwards. So the moment caused by these 300 newtons going to negative j is going to be, let me use a red for moment. In this direction, which is aligned with negative k. Make sense? All right, so the way you determine the direction of the moment is you use your right hand, which is the 4 fingers will be the direction of your force, and the thumb is the direction of the moment. Let me give you a very easy example. So for example, this end is fixed, and I say this is there's a force going downwards, right? So if force is going downwards, and this point O is the pinpoint, the moment direction will be using your right hand, right? 4 fingers. These 4 fingers going downwards align with your F. while your thumb will be the direction of the moment, which is go into the paper, right? Okay. So which is go into the paper, we use this, right? Okay. If I say, in other words, I'll draw it three-dimensional, so it's easier for you to understand. If I have a beam and at the end it's fixed, I have a force applied over here. I have X, Y, and Z. So in this case, if this point O is fixed, the force is going to what direction? Oh, sorry, the moment is caused by the force is going to what direction? Negative Z. Sorry, what? What? Negative X, right? See, this force is going downwards. So use your right hand. It's going downwards, and the thumb is pointing into the paper, which will be this direction, negative X. Make sense now? Kind of? Okay. Alright. We'll learn as we go, okay? Alright. I guess I need to explain more. Okay, so this we know, right? X, Y, Z, we have I, J, and K, right? Three-dimensional unit vector. Okay, so if this end is fixed, I have a force pushing up. It's going to, let me not say it's fixed. Just say this thing is simply supported at the end, so it can rotate, right? So if this force is going upwards, this force will cause a moment, right, for this beam to rotate. So how do I determine the direction of the moment? You use your four fingers to align the direction of the force, right? And then it's going that way, right? So the thumb, of course, is going to moving outside of the paper. So it is the same direction as your X. So this M will be in the direction of I. Make sense now? Okay? Right? So use your four fingers as your rotational direction. So rotation goes from bottom to top, which is aligned with the force. Thumb, use your right hand only, okay? For those of you who are left-handed, don't use your left hand. Okay, so the thumb is direction of the moment, right? So of course it's coming out. Once it's coming out, of course it's aligned with the positive X. So therefore the M is in the direction of positive I in this case. Make sense now? Okay, all right. All right, now let's look at this case. Again, the coordinates keep it in mind. All right, X, Y, and Z. X going this way, aligned with AB. Y going up, and Z going to that direction. All right. So we only look at this small cylindrical ball over here. First thing first, we start with simple, right? So the force is 300 newtons. Of course, this Fc, the force resultant force on point C, when you take this small ball out, will equal to 300 newtons. That's easy to understand, right? Okay, so summation M is also 0. So therefore, I know the moment caused by these 300 newtons will be equal to 300 newtons times the distance, which is 1.5, because this distance over here is 1.5 meters, right? So therefore, this moment caused by the 300 newtons will be equal to that direction, which is, we come here for direction, it's opposite direction of k, so therefore it's negative k. Make sense now? All right. So the quantity equals to 450 unit Newton times meter, and the direction over here. So the red is what generated by the force, which I'll show you over here. This force is calling it. Let me use orange. Therefore, at this point, there's gotta be a bending moment to balance for it, which is in the direction of positive k. So this MC is equal to 450 k Newton times meter. Answer. So therefore, what you have here is you have a force 300 newtons, or let's say minus 300 J newtons. This resultant force will be 300 J newtons, and you also have a bending moment that equals to 450. Newton times meter. This is the free body diagram of that small cylindrical rod where the force is applied. Make sense? Yes? Okay. Any questions? Feel free to ask questions, okay? Because it's becoming complicated. Yes?
Double arrow? Moment?
Yeah. Double arrow means moment or torque, which we'll see later. Okay? All right. And single arrow just means it's force. Okay? And we know why the direction is this, right? Because this red is the bending moment caused by the force. So you gotta have an orange over here to balance for the red, which is the bending moment existing at point C. So therefore, the free body diagram you have is this. So everything is under balance now, right? Force and the force cancel out. Bending moment over here will counterbalance for the bending moment caused by this force. Okay? All right. Okay, now we can move on. So the next thing will be, let's look at BC, because the small cylindrical rod, a handle, or ball, whatever you call it, is connected with BC. Okay, so let's see BC here. BC. Okay, so point C and point B. Now again, this is your Y direction. This is your Z direction. Okay, just be clear, because this direction still applies, right? Y is going up, Z is coming along the same direction as BC. So I am going to use arrows. Okay. All right. Now, see this. When you first analysis this point is C, right? And also, this point C is on both the ball handle, and it is also on this BC. So therefore, whatever the reaction force and the bending moment here will be applied here as well, because for point C, it is under equilibrium. So summation whatever at point C should equal to 0. Summation whatever moment at C should equal to 0. Okay, another way to think about it is Newton's third law, right? When you have a force going up, at the same point, of course, you're going to have a force that is going downwards, which equal to the same magnitude, different direction as this force over here. Okay, so this will be minus 300 J newtons. Agree? Okay. Now, also, of course, you have a moment over here, right? Going to positive z direction. Of course, I am going to have a negative z to balance for this internal moment here, right? Okay, so you will have a bending moment that equals to minus 450 the direction of k. Newton times meter. And I said I'm going to use different color, huh? Therefore, you can see it better. Okay, so 450 over here, right? Does it make sense or not? Kind of? Yes? Okay. All right. Because everything... Inside C, everything should be on the equilibrium. So therefore, here's 300 going up, and here's 450 going to positive Z. You have 300 going down, negative Y. You have 450 going to negative Z to balance for you, right? Therefore, all the stuff inside here at point C is on the equilibrium. Because this is point C as well. This is point C. So at one point, of course, we look at it, everything is on the static condition, so it's going to satisfy the equilibrium conditions, right? Okay. All right. Now, once we have point C, we come to point B over here. Okay, so BC is on the equilibrium, right? Okay. Therefore, at point B, you will have a force of 300 J newtons. That's to balance for this force, right? And also, in the same time, you will have something going to positive z direction to balance for that 450 K. Right? So it has to, on the equilibrium, summation F is 0 and summation, the moment is 0. Okay, now there's one thing I need to mention here. First of all, let's see this. Remember we learned the concept of torque, right? So this is easy to understand. Everything's on the bending. Right, so this moment, which is 90, direction of the moment is 90 degrees to the beam. See it? See this? This double arrow, the red one, is 90 degrees to the beam, the physical beam over here, right? While in this case, this BC, the moment, the double arrow, the red color one, is in the same direction with the beam, right? Now, do you know what kind of deformation is this moment going to cause? It's going to cause probably twisting. Yeah, that's a torsion, right? So imagine you have a beam going this way. Now, like I said, a torque is like this, right? Torque. So the way, let me draw it the other way. This is what we learned 2 days ago, right? So if a ball is like this, you have a torque applied to it. You can also determine the direction. It's also the same. Use your right hand. So this is direction of your torque. Use your 4 fingers to be the same direction of the torque. Your thumb is the direction of the torque, which in this case is this, and this one goes this way, right? So if the moment is in the same direction of your beam member, it is torque. If the direction of your moment of the is 90 degrees or is perpendicular to the beam moment, it is bending. Okay, so in other words, we have two types of moment. It has same unit of Newton times meter, right? Remember? So one will cause bending. The other one will cause twisting. So that's why we call them bending moment, or sometimes we could just call it a torque, because it's going to cause it to rotate, right? Make sense now? Okay. So I'm going to erase this. Okay, now the interesting thing is here. See, this small handle and BC, they're 90 degrees apart. Therefore, when you have a bending moment in the small beam over here, let me just call it CD so I don't have to keep on calling it. So this CD and the BC, they have one point in common, which is C. But on point C in the member of CD, it's bending, right? It's going to bend it because it's 90 degrees. While the same moment for BC is going to cause BC to twist. That's a torque. So this bending over here is the same as the torque over here in terms of quantity, magnitude, 450. Make sense? Which, if you look at this picture over here, you can also understand. See, when you have a fixed end at a point C and everything is all fixed, F is probably going to cause this CD to go down, right? But in the same time, it's going to twist the BC, right? Because imagine if you apply a force over here, BC is going to be twisted, while this CD over here is going to bend down, right? So that totally makes sense by doing the force analysis here. So 90 degrees bending, 0 degrees torque, okay? All right. So when we say torque, we use T. We don't use bending moment anymore, all right? So summation T equal to 0. Therefore, we get these two numbers, right? Now, because, there's nothing I need to write over here because we are already familiar with free body diagram. So that's why I write out of this number directly. But you shouldn't know why it's 300, right? Because summation F is 0. Therefore, it's 300. Just different direction, okay? All right. We should be good, huh? All right. So, are we done with BC yet? Is there anything we missed? Anything we missed about BC? I think there's one thing we missed. Huh? It's bending in negative J. Negative J. I'm not sure. Okay, but you can't get the point. It is bending. Huh?
About the x-axis.
Right, exactly. So, why is that? So, see here. When we treat CD, CD is a cantilever beam, right? But in the same time, BC is also a cantilever beam, right? Because B is totally fixed, connected to the A, but C this time is free. So, we have a cantilever beam over here. So, imagine this point, this blue point over here, is your fixed point. This force over here is also going to cause some bending, right? So we also have summation M equal to 0 in this case. for BC. So summation m equal to 0. I know this time let's choose blue. This force is going to cause some bending moment at point B in the direction of here. Right? You still use your right hand. 4 fingers going downwards, thumb going back. So that is negative x direction, right? So the magnitude will just equal to 300 times the length of BC, as we mentioned, is 4 meters. So that equals to 1200 Newton times meter. So I do the calculation here only on magnitude, as you can see, right? Because directions, I just see it from the plot, from the figure, okay? So this is 1200. And this is in the direction of negative I, right? Let me see, yes. Also has a unit, Newton times meter. Okay, now, again, same thing. This blue bending moment is caused by this blue force over here. So at point B, you gotta have a bending moment to balance for it, right? So balance, I'm going to use purple over here, which is in the same magnitude but different direction. Therefore, the value is 1200 I Newton times meter. Okay, so this is what the internal force will be like inside the beam BC. Okay? Now, if I write it, use everything in black, it'll be negative 300J newtons, and then we have minus 450K Newton times meter. And over here, you have 300J Newton force to balance for the force, and also same time you have a 450K of torque, and at the same time you have a bending moment caused by the force, right? So BC, this is what it looks like. So at point B, you have negative 300 J newtons force going down, and also 450 in the negative K. While at point B, you have 450 K going to positive K, and then you have 300 J Newton force going upwards, and then 1200 I of a bending moment going to the positive X direction, right? We get it or not? So there's 3 components here and 2 components here, right? I guess the only thing a little tricky is where the 1200 purple color is from, because it is to balance for the blue bending moment caused by the force at point C, because BC is a cantilever beam as well. Okay? All right?
Those are the exact same beams, right? BC and...
Huh? Yeah, I'm just trying to...
oh, you just redrew it?
Yeah, I'm just trying to get rid of this black, this blue, because if this blue is caused by this force, it doesn't apply on the point B. In reality, you don't have this, but the reason why I drew it here is just to help you to understand why this 1200 I is going to this direction. Okay, make sense? All right. So just remember, all these reaction force existing because they're trying to balance for it, because everything is on the equilibrium. Now, everything goes to three-dimensional. Not only we have force and moment, we also have torque equal to 0. So don't forget to do these three. Okay? Make sense? All right. Okay, so lastly, let's look at AB. Okay, now AB, first of all, point B. Now, like you see over here, this B has three different components. You have a force going upwards in the direction of J. You have a torque equal to 450 in the positive K. You have bending moment of 1200 I, Newton times meter, right? So three component in point B. In the same time, point B is also on AB, so you use Newton's third law. Everything should be inverse in direction, but same magnitude to balance for the internal component of B over here, right? So automatically I know on point B, on the member of AB, you'll have a force so for point B on AB, summation F is 0, summation M is 0, summation T is 0. Okay, still same thing, right? So first of all, summation F is 0, so you have a force of 300 J newtons, right? So that's because of this, okay? F is 0. Now, in the same time, you have summation M is 0. So whatever over here, you have 1200 I Newton times meter. And in the same time, you have negative 450 K Newton times meter, right? So let's compare point B over here and point B over here. So force, that's easy. You go up, I go down, right? So this torque over here, 450, which is positive K. So therefore, you have negative 450 K. And here you have 1200 I. So therefore, I have a negative 1200 I to balance for everything. So now, if we add everything together, all equal to 0, right? Yes? Okay. All right. Now, another thing I need to point out is, see here, the 450K is the torque over here, right? But see here, this 450K is 90 degrees to the beam AB. Therefore, this minus 450K is what? It's bending, right? It's going to cause it to bend. And this 1200I initially is bending to BC, but this time it's 1200I, which is in the same direction as AB, therefore it's torque. Make sense? So AB and BC and CD, they're all 90 degrees apart, so therefore bending moment to one of the member will just equal to the torque to the other member. Okay? All right. So next thing will be finding out everything for point A, right? For point A on AB, we do the same thing. Summation M is 0 and summation T is 0. Okay, so first of all, force is easy, so you have a negative 300. You gotta have a positive 300. So 300 J newtons right? So that's because of a force, summation is 0. So the next thing will be you gotta have some moment to balance for the torque and the moment. Okay. All right. So should I have something here? That equals to 1200 I Newton times meter. That's to balance for the torque over there, right? And you gotta have something called 450K. Newton times meter. And again, just be aware, this is I, this is J, this is K. So this is your directional vector, and don't forget that, right? If it's go against to the negative I, that's why it's negative I, right? If it's going downwards, that's why it's called negative J. It's because directional vector is like this, okay? All right, that's 4.8. Are we done yet? There's one more thing, right? Which is the bending moment caused by the force, because AB is a cantilever beam. A is fixed, B is free. Because we sectioned it into three different members, right? Free body diagram is to analysis of force, moment inside each member individually, right? Okay, so this free body diagram, A is fixed, B is free. So therefore, this 300 J Newton is going to cause a force which is going to cause a bending moment going to this way, right? In the negative K direction. Okay, so you will have a bending moment at a positive K to balance for that. So summation M is 0. Therefore, you have something extra. I'm only writing out extra, okay? Equal to 300 magnitude only times the length. I believe it's 5, but let me double check. Yes. 300 times 5, that's 1500 Newton times meter. Okay, and it's in the same direction as what's existing. So, let me get this red. So they equal to 1500 in the direction of K, Newton times meter. Now this red is to counterbalance for the moment caused by the force. Okay? Alright, so the total bending moment at point A should equal to 450K plus 1500K. They equal to 1950K Newton times meter. Okay, because they add simply, right? Okay. Let's see. So, do you guys have any questions? Any questions about this? So, all we need is this free body diagram over here. Oh no, I'm not going to erase it. This thing over here. This is for member AB, and this thing over here, which is for BC, and over here is for CD. Okay, so these three is what it is asking to ask you for the resultant force existing inside of each member, and also directions. Right, this is how it works. So all we are using, the key we are using here these equations. Summation F is 0, torque 0, moment is 0, right? And there's only one more thing you need to keep in mind is for each member we analysis it, each one is a cantilever beam. So don't forget to add an extra bending moment at the end.
Copy the last part.
This one?
Yeah. Well, the very bottom.
Total bending.
Okay. No problem. Alright, so that's the key. Still equilibrium, but going to three-dimensional, just have one more turn other than force and the moment, right? There's something called torque. And also, don't forget each time we look at only one member, that's a cantilever beam. So make sure you add an extra bending moment at a fixed end. And that's pretty much it. The rest of them just the math, right? Okay? Alright. Do you have any questions? Are we going to see this in exam? Yes, absolutely. Right? Okay. All right. Now we have about 10 minutes. Yeah, I guess we have some time. Anyway. Okay, so the question B is asking for the maximum torsion stress and bending stress in BC, right? You guys don't want to learn anymore, huh? Tired of the big example, huh? All right. I guess I can stop here because the next one is also quite big. So we'll continue the example on Tuesday, all right? But make sure you understand this, all right? Because it's important. It tells you where the maximum moment is and where the maximum force is, right? Okay. Well, I'll see you guys on Tuesday, right? Okay. All right.